Hi, I'm David, and I want to talk about robustness of deep neural network weights against random bit errors in order to enable energy-efficient DNN accelerators. I'm from the Max Planck Institute for Informatics, and this is joint work with Bernd Schiele, Matthias Hein from the University of Tübingen, and Nandini Chandramurthy from IBM. DNN accelerators generally feature on-chip SRAM, which is used as scratch pads to store DNN weights. Data access and movement usually makes up a significant part of the accelerator's energy consumption, and so reducing the voltage of the involved SRAM arrays has become interesting to improve energy efficiency. As shown here, energy consumption per SRAM access can be reduced significantly when reducing voltage. Note that both axes here are normalized by Vmin, which is the lowest measured voltage for error-free operation. However, these SRAM arrays quickly become unreliable when reducing voltage. This is illustrated here for two voltage settings, and these maps show the bit error rate, or the bit error probability, per bit cell for a small portion of the SRAM. Note that the rate increases with reduced voltage. In practice, this will directly affect the stored DNN weights. In fact, the bit error rate can be shown to increase exponentially, as shown in blue here. Note that the left axis is in log scale. This means that the DNN has to endure exponentially increasing rates of bit errors in its weights in order to reduce voltage and energy consumption. Unfortunately, this results in significantly increased test errors. This plot shows the robust test error at various bit error rates. The robust test error is the test error measured after injecting random bit errors in its weights. Note that the change in axis. Now the x-axis shows bit error rate in log scale. Note that the robust test error increases very quickly for this normal trained model using 8-bit quantization on cipher 10. We consider a simple but realistic bit error model. We assume bit errors to be distributed uniformly at random across spatial locations. While the bit errors can be assumed fixed for a fixed voltage and chip, they are assumed random across voltages and chips. Also, the bit error at higher voltage for a fixed chip, meaning lower bit error rate, usually forms a subset of those at lower voltage, meaning higher bit error rate. Based on this model, we propose a combination of 3 methods to improve robustness of DNNs against bit errors. First, we consider a robust fixed point quantization. Then we consider weight clipping during training as a regularization. And we propose random bit error training, meaning training on completely random bit errors. In contrast to related work, our approach generalizes across chips and voltages and allows to reduce energy consumption with little to no increase in test error. Compared to standard fixed point quantization, we reduce quantization range and also consider the impact of implementation details. We found that these quantization details can have significant impact on robustness while not affecting clean test error. We found that as a result, our robust quantization reduces robust test error significantly, as shown here in brown. However, for high bit error rates, test error is still very large. Second, we use weight clipping during training. This means that during training, the weights are explicitly constrained to a small interval. We found that this regularizes the DNN to learn more redundant and so also more robust weights. As can be seen here, weight clipping further reduces robust test error, especially for very high bit error rates. Finally, we combine weight clipping with random bit error training. Here, we inject completely random bit errors during training to further improve robustness. Note that this comes at a slight cost of clean test error, as shown on the left, but further reduces robust test error at high bit error rates on the right. Note that the increase in robust test error is, for example, below 1% for a bit error rate of 0.1%, as marked in red. This would already enable an energy reduction of roughly 20%. Higher reductions in energy consumption are possible at the cost of a higher robust test error. In black, the lowest robust test error achievable for each bit error rate is highlighted. Note that for low bit error rates, robust quantization and weight clipping alone are quite effective. For higher bit error rates, however, random bit error training is essential. Our approaches can easily be combined with lowering the precision. This results in large energy savings from both low voltage operation and lower precision. As can be seen here, going from 8 to 4-bit on cipher 10 results in an insignificant increase in robust test error at all bit error rates. This is the dashed black line shown here. In conclusion, we consider a uniform bit error model that realistically captures the nature of low voltage induced bit errors across voltages and chips. We propose a robust quantization scheme, weight clipping, and random bit error training to improve robustness considerably. In our paper, we provide additional results on MNIST and cipher 100, guarantees, and show that we generalize to bit error distribution significantly different from our model, as shown on the top right, for a profile chip where the bit errors are strongly aligned along columns. If you have any questions, feel free to ask them during the Q&A or can contact me through my webpage.